steady-state conduction in one dimension. All right, if you're a first-year chemical engineer, this is for you. This material is your foundational model for simplifying what looks like really complex heat flow, in things like walls and pipes. The whole thing hinges on one core idea, that heat flow acts just like an electrical current, and it's all governed by something we call thermal resistance. So let's break it down into 3 key takeaways. First, for a simple plain wall, the big move is to treat its physical properties, its thickness and its material conductivity, as a single value called thermal resistance. This is a game changer because it lets you analyze walls with multiple layers just by adding up those resistances in a series. Yep, exactly like you would in an electrical circuit. Second, we expand this model to cover radial systems, which is super important for things like process pipes and tanks. Here, the area the heat flows through actually changes as you move outwards, so the math for thermal resistance needs a logarithmic term to account for that. This is also where the R value you hear about for home insulation comes from. It's just a practical way to measure insulating performance. Finally, we have to account for fluids, which means dealing with convection boundary conditions. We can actually model this with its own convection resistance. So now we can combine everything, all the conduction and convection resistances in series, to get a total resistance. This leads us to the overall heat transfer coefficient, or U value, which is absolutely the key metric for calculating heat transfer in real systems, like heat exchangers. So really, these foundational one-dimensional models, built around that electrical analogy and thermal resistance, are absolutely essential for solving real-world heat exchanger and piping problems. Let's dive into more detail.
All right, let's dive into a really cool concept in heat transfer, one-dimensional conduction. We're going to break it down using a super simple analogy that, I promise, is going to make everything just click.
So you see it all the time, right? A thick wall keeps your house cool in the summer, insulation keeps your pipes from freezing. But, how does that actually work? It seems kind of complicated, but what if I told you we could think about it just like a simple electrical circuit?
Okay, check this out, because this is the secret to the whole thing. Over on the left, you've got Ohm's law. You've probably seen it a million times. The flow of electricity, or current, is just the voltage difference divided by the resistance. Now look at the right. Fourier's law for heat transfer is, well, it's pretty much the same thing. The flow of heat, Q, is driven by a temperature difference, and it's opposed by something we call thermal resistance. This is no accident. It's an incredibly powerful way to solve heat transfer problems.
So here's the game plan. We're going to really nail down this Ohm's law analogy first. Then we'll look at the basic resistors you'll see all the time, like walls and pipes. And finally, we'll put it all together to build and solve complete thermal circuits for systems you'd see in the real world.
So, let's just make sure we've got this straight. In electricity, voltage is the potential that drives the flow. In heat transfer, temperature is the potential. Heat always flows from a higher temperature to a lower one. The material that it has to flow through, that's our resistance.
So the whole point here is that materials don't just kind of block heat. No, they provide a very specific, measurable resistance. If something has a high thermal resistance, it's a great insulator. If it has a low thermal resistance, well, it's a great conductor. Simple as that.
All right, let's build our first component in this thermal circuit. We're starting with the most basic building block you can imagine, a simple flat wall.
So just picture a sheet of glass or a concrete wall, whatever. It's got some thickness, right? A certain area that heat can flow through. And every material has this property called thermal conductivity, K, which just tells you how easily heat can move through it. And in our circuit analogy, this whole wall just becomes one simple resistor.
Now this is what I love. This formula just makes sense. Look at it. If you want more resistance to stop more heat, what can you do? Well, you can make the wall thicker, increase delta X, or you can use a material with a lower conductivity, K. Makes sense. But what happens if you increase the area, A? Well, you're giving the heat more paths to take, so the overall resistance actually goes down. It's totally intuitive.
But of course, the world isn't all flat walls. A huge part of chemical engineering involves pipes and cylinders. So let's look at our next common shape.
Now, here's the key difference with a pipe. As heat moves from the inside to the outside, the area it's flowing through gets bigger and bigger. The heat literally has to spread out as it travels. And because that area is changing, our formula for resistance needs to change a little bit too.
And here's the formula that captures that geometry perfectly. Now, don't let the natural logarithm there scare you. All that term is doing is mathematically accounting for the way the heat has to spread out as it moves from that small inner radius to the larger outer radius. It's just a way to handle the geometry.
Okay, now for the payoff. This is where the magic really happens. We have our basic resistors. Now let's see how we can combine them to analyze the more complex, multi-layered systems you'll actually see out in the field.
This is the best part of the whole analogy. Let's say you have a wall that's made of brick, then a layer of insulation, and then drywall on the inside. The heat has to get through the brick, then through the insulation, then through the drywall. That's a classic series circuit. And to find the total resistance, you literally just add them up.
So it boils down to this super simple four-step process. First, you just identify all your layers. Then you draw it out as a simple circuit diagram. Third, you calculate the resistance for each individual layer and just add them together. And finally, you use our Ohm's law for heat to find the total heat flow. It turns a complex problem into basic addition.
So far, we've only been talking about conduction. That's heat moving through a solid object. But that's not the whole story, is it? We have to figure out how the heat gets to the wall in the first place and how it leaves on the other side. And that process is called convection.
Yeah, think about it. There's a little bit of resistance for the heat to get from the warm air in a room onto the surface of the wall. And then on the other side, there's another resistance for the heat to get from the outer surface of the wall into the cold air outside. So what does that mean for our circuit? It means we add two more resistors, one at the very start and one at the very end. And this brings it all home. The total heat that makes it all the way from the hot fluid on one side to the cold fluid on the other is just the total temperature difference divided by the sum of everything in its way. That means the convection on the inside, all the conduction layers in the middle, and the convection on the outside, all added together.
Now let's be honest, adding up all those different resistances every time can get a little repetitive. So to make life easier, engineers came up with a handy shortcut, the U-value. The U-value basically just bundles all of those resistances together into one convenient number, giving us a really fast way to do design calculations.
And looking at some real numbers, you can see why this matters so much. Remember, a lower U-value is better. It means higher resistance. Look at that old concrete block wall, a U-value of 1.83. Pretty bad. Now compare that to a modern, super-insulated wall with a U-value of just 0.17. Wow, that's a huge, huge improvement in performance.
So, what's the big takeaway from all this? The most crucial thing is that you can model really complex systems as just a simple circuit. Walls, pipes, insulation layers, they're all just resistors. You figure out the resistance for each piece, conduction and convection, add them up in series, and you can predict the total heat flow. It's an incredibly powerful tool.
And I'll leave you with a fascinating little puzzle to chew on. When you add insulation to a pipe, you're adding conduction resistance, which is good. But you're also increasing the outer surface area, which can make it easier for heat to escape via convection. So, is it possible that adding a little bit of insulation could actually make heat loss worse? It's a famous problem called the critical thickness of insulation, and it just goes to show how powerful, and sometimes kind of weird, this whole resistance analysis can be.